everyone. Welcome to another Tea Time Talk. We are now on our 40th session, and we are very happy. Oops, I got a little bit of a lag going on here. Do you have a... Okay, no, wait. That's better. Welcome again to our 40th session of the Porous Media Tea Time Talk. So we are part of the Interpor Academy, and we are very happy to welcome you to this session. Today we are having a session that is a little bit later on the European time, and that's because we wanted to focus on our viewers and on our audience in the US. So this is we have two speakers from the US today, and we are going to start with Joanna Schneider. So Joanna is from Princeton University, and she's a fifth-year PhD candidate and Matter Graduate Fellow in the Department of Chemical and Biological Engineering at Princeton University. She's working together with Professor Sujit Datta and Rod Priestley. Her PhD work focuses on interactions between colloids and immiscible fluids in porous media to inform colloidal particle design for groundwater remediation. So Joanna, we're going to put you up on the screen now. Yes, and whenever you're ready, the floor is yours.
Okay, great. Thank you so much, Marcel, for the introduction. Hello, everyone. So today I'm going to tell you about a simulations project that I've been working on that's motivated by experiments to describe how deposition and erosion of colloids is impacted by immiscible fluid transport in porous media. And so before I jump into the details of the project, the primary motivation of most of my work is both the national and global need for clean water. And so in the US alone, nearly 40% of us get our drinking water from groundwater aquifers, but hazardous waste sites across the country frequently have contact with our water supply. And so when those water supplies are in contact with these hazardous waste sites, they are often contaminated with immiscible contaminants. And in fact, 60% of these Superfund sites on the EPA's national priorities list are contaminated with oil-based contaminants like halogenated hydrocarbons. And so in order to address this problem, prior to the 1990s, commonly what was used were these pump and treat remedies in which contaminated water was removed from aquifers and then placed in tanks to be treated. And so in the last 20 years or so, practitioners have hoped to solve these problems without removing water in a batch process and instead use in situ mechanisms in which an additive can be pumped directly into an aquifer. And so examples of some of those additives are polymers, surfactants, and colloids. And we look at colloids because they hold promise for a variety of applications, and also they can be engineered. And so some of those applications include groundwater remediation, as I've mentioned already, contaminant transport, enhanced oil recovery, the list kind of goes on and on. But from a fundamental standpoint, to study colloidal flows and interactions between colloids and immiscible fluids, simplifications have often been made due to the complexities that arise in these systems. And so both in our group and in other research groups, there's been progress in learning about more complex forms of colloidal transport and interaction with immiscible fluids. And so one example shows a study that came out of our lab where we can directly image multi-layer, so dense aggregated deposition in single phase flow. And we find that we can access different regimes of colloidal deposition by changing the flow conditions. But other studies have looked at both computationally and experimentally how single particles interact with immiscible fluids. So in this first study, we don't have the presence of an immiscible fluid. We don't know how this transport process would be impacted by that. But in this second study, what we can see is that really complex behavior arises just when you look at a single particle in flow with an immiscible fluid. And so what you'll see is that this particle here will get pinned by the oil interface. Eventually, it will get pushed into the bulk. And so we've learned a lot from these studies, but we're still missing the answer to a key question. And so if we sort of combine the framework of both of these studies, can we observe what happens as an immiscible fluid travels through dense deposits of colloidal particles? And that's the question I'm going to try to address today. So originally, we wanted to answer this question using one of our lab's primary capabilities, which is 3D experiments. But it quickly became clear that this was not going to be the best way to study this problem because of the complexities that arise in these geometries. And so some examples of these complexities include this in situ Pickering emulsification, where we see these oil droplets get stabilized by colloidal particles as they flow and they break up and they get trapped there. Another complexity that we see is that as the fluid is traveling through the porous medium, it often has to break through some critical deposit or some critical yield stress in order to percolate through the medium. And so while these are really important complexities to be able to observe, it makes sort of decoupling the physical phenomena that are going on really challenging. And so in order to pursue a simpler line of questioning, we wanted to turn to a combination of simulations and simplified experiments to answer the question of how colloids impact immiscible fluids as they move. And so we decided to use two-dimensional pore network modeling to do this. And so we generate a modified invasion percolation simulation that could describe some of these complex deposition and erosion processes that arise due to immiscible fluid flow. So very simply, invasion percolation, if you're not familiar with it, is a simple mathematical model that describes immiscible fluid invasion in a porous medium, and it follows only one rule. So if my immiscible fluid invasion starts here at the star, it can invade any of the attached pores, and it will always pick the largest pore or the path where the capillary pressure threshold is the lowest. And so that's the only rule for this simulation. The only other stipulation that we incorporate is fluid incompressibility, which means that each time the immiscible fluid moves forward, it's going to have to displace the fluid in its way. And so if there's nowhere for it to go, like here, it can't invade that pore. And this process is referred to as trapping. So now we're going to incorporate the physics of deposition and erosion. So we have to account for our particle deposition process. And the way that we do that is by running some simplified pore scale experiments in a capillary tube. And so to isolate those key physical mechanisms, what we're going to do is coat a single capillary tube with colloidal particles to model a single pore, and then we can flow a single oil droplet through it. Now, when I play the video, I'm only going to show the fluorescence from the particles as I showed, because as I showed in 3D experiments, what you'll see is that the particles will localize at the oil interfaces, and that will allow you to see them. And so this system is still very complex, but there are sort of two key observations I want you to make, which is that the interfaces can both pick up and drop off colloidal particles. And obviously there are additional complexities, as I've already mentioned, but those are the only things that I want you to focus on because that's what we're going to incorporate into our simulations. So we can do the same thing that we do in our experiments. In our simulations, we can coat an edge or a pore throat with our colloidal particles. And then we can define this deposition as some kind of film thickness TD. And this tilde TD is simply a normalized value that's normalized by the maximum pore throat radius in our system. And we have a uniform distribution of pore throat sizes in the system. So then this tilde R effective simply becomes the effective radius of each pore due to deposition. We can then incorporate this erosion piece by thinking about the balance of stresses at the oil interface as it travels over these particles. And so interfaces pick up particles when the capillary stress exceeds the yield stress of the deposit. And so we can define a ratio of those two quantities as an erodibility, which essentially says when my capillary stress exceeds my yield stress, I'm going to erode something. And so this now sets a rule for when we have erosion as well. The last thing that we have to account for is redeposition. And we simply do that by assuming that all eroded volume is deposited proportionally in the pores immediately connected to it. And so this framework allows us to change our simulations simply by changing two parameters, this deposition TD and this erodibility E. So now to observe how deposition and erosion are actually modifying our immiscible fluid invasion pattern, we can measure the filled volume fraction in each simulated network with the immiscible fluid and compare it to standard invasion percolation or capillary fingering. So we can look at how it deviates from capillary fingering. Keeping the erodibility constant, here we're looking at no erodibility, and increasing the amount of deposition from pristine to clogged. What we see is that almost all of our simulations look exactly like capillary fingering. So I can pick anything sort of along this line. And this is for a single network when we have a deposition thickness of 0.25, 0, 0.8, they'll all look exactly like this. But once we get closer to complete clogging, we see this sharp transition. And so what that tells us is that in the absence of erosion, the invasion patterns will remain unchanged until some of the pores begin the simulation already clogged. So now I can show you another case where we have an erodibility that is much larger. So here we have softer deposits that are actually erodible. They'll start to move things downstream. And what we see here, I'll just point out that the blue-green line is for a single network and the purple is a general trend. Here, the general trend and the single network overlapped, so you couldn't see them. But if I show you the same network with an erodibility of 0.8, we see something drastically different, which is that over a certain range, so generally over a certain range of TD values, we are actually accessing more of the pore space than we do with standard capillary fingering alone. And in this specific example, we can compare them directly, and we can see that the filled volume fraction is much greater when we have erosion versus when we don't. So I want to show you one final result, and that's that we can take these results one step further to explore the entire deposition and erodibility state space. And so here we see three distinct regimes. We still have this capillary fingering regime in green. We have what's called a rapid clogging regime, and that corresponds to this network here. And then we have the emergence of this new regime, which we're calling erosion-enhanced fingering. And so what we wanted to accomplish by using simulations was have a powerful predictive tool, right? And so we wanted to determine analytical expressions to describe the transitions between each regime. And so we found that by answering really simple questions, we could do just that. And so in order to determine the transition from capillary fingering to erosion-enhanced fingering, we simply ask, when does rearrangement begin? And that's going to happen when the capillary stress in the largest pore exceeds the yield stress of a deposit. We can rearrange this in terms of our dimensionless parameters, and we see that we have really nice agreement. We can really clearly delineate the boundary between capillary fingering and everything else. So we have another boundary here between erosion-enhanced fingering and rapid clogging. And in order to determine that transition, the same logic follows. We just ask another simple question, which is, when does clogging begin, right? And so simply put, when the amount eroded from a parent pore exceeds what its children or connected pores can take, they'll start to get clogged. So the math here becomes a little bit trickier because we have a distribution of pores. But as a first approximation, if we assume that all of the pores have the same size and everything expands out radially, we can simplify the math and come up with sort of an upper limit for where we're going to see that erosion-enhanced fingering regime. And that winds up being this expression here. And what we see for the networks that we've looked at here, which have a fairly narrow uniform distribution of pore sizes, this first approximation works reasonably well. And so I hope that what I have shown you today is that under certain deposition and erosion conditions, an immiscible fluid can actually access more of the pore space than via a traditional invasion percolation regime. Also, this framework allows us to predict invasion patterns using two simple parameters. And so in the future, what we're hoping to do is govern experiments using these parameters, both in our pore scale and our more complicated 3D experiments. And I just want to take a quick moment to acknowledge all of my collaborators. I worked with two other wonderful graduate students, Chris Brown and Daniel Amchin, and two really talented undergraduates, Malcolm Slutsky and Cecilia Quirk, and my advisors, Sujit Dowd and Rod Priestley, and our funding sources. And with that, I'd be happy to take any questions. Thank you so much for listening.
Wonderful, Joanna. Thank you very much. That's a super interesting. I welcome the audience to write the questions down in the comments field so we can read it here. In the meantime, I have one myself.
Sure.
So when you tune the parameters down to zero, so no erosion, no deposition, then you're back in the classical
Exactly.
invasion percolation regime, right?
Mm-hmm.
So did you measure how did the fractal dimension of this invading cluster change with these parameters? Because suddenly you have like a continuous parameter that you can tune, and that could have an effect over the fractal dimension.
Yeah, so that's a great question. We did measure the fractal dimension. We didn't see a huge change in that quantity over the capillary fingering or erosion-enhanced fingering regime. So I think that the whatever that standard value is for capillary fingering, it didn't change much in that erosion-enhanced fingering regime. And then once we get to the rapid clogging, that's kind of a parameter that doesn't mean much. But we're still trying to figure out why it hasn't changed significantly, because the invasion patterns change a lot. So that's a great question. But the short answer is we're not sure yet why it's not super different.
Right. What about like the trapping of clusters? Did you notice any difference with like this? Sometimes like you have like trapped of the defending phase clusters that are the trapped clusters of the defending phase that are left behind. Does it change in any way with this with the erosion and the position?
So the fact that the fractal dimension hasn't changed much signals to us that the amount of traps that we see also hasn't changed very much. And in general, I would say no, we didn't see that a lot. We'd have to look more at individual networks to see that. In the single example I showed, those traps seem to become a little bit smaller but there are more of them because we're exploring more of the pore space. So again, it's an interesting question. It makes me think that there's some kind of interplay between the change in size of the traps and the number of them. And so as we're exploring more of the pore space, we have more traps, but they're smaller. But yeah, that's another great thing to look at. This is ongoing work, so I appreciate those questions.
Super. That's excellent. It's very good work.
Thank you.
We have one question from our audience here. So Catherine Spurring asks, will you be expanding your work to 3D? How accurately do the predictions, example, start of clogging, match 3D observations?
Yeah, so that's a great question. The simulation work right now, we don't have plans to expand them to 3D. We don't anticipate that the results for the pore network simulation would change very much. As far as the experiments versus like the pore scale experiments versus the 3D experiments, we do see a pretty significant difference in how much deposition you need in order to get sort of more interesting things to arise. So like the clogging regime, or the regime where you get sort of interesting rheological behavior of the immiscible fluids, those change a lot from the sort of simple cylindrical capillaries to the 3D tortuous geometries.
Right. Super. So do we have any other questions here in the studio or in the audience? So far, I don't see any, but if there are any extra questions, please feel free also to contact the speaker directly after the talk, or you can leave it in the comments here and we can forward to them. Okay, thank you very much, Joanna.
Thank you so much.
Now we move on to our second speaker of the day, and that will be Kyle Pietrzyk from Stanford University. So Kyle is a fifth-year PhD candidate working with Professor Elena Battiato in the Energy Science and Engineering Department at Stanford University. His research involves automated multi-scale model development for reactive mass transport in porous media and energy applications. When he's not doing research, Kyle enjoys running on the beach, backpacking, playing tennis, and bouldering. Okay, so Kyle, if you're ready, the floor is yours.
Awesome. Thank you so much for the introduction. So yeah, I'm Kyle, and today I'm going to be talking about some of the work I've been doing the past couple of years regarding automated multi-scale model development using symbolic computing. Let's see. Okay, so yeah, looks like my slides are. Okay. Yeah. Do you know if I could share my slides instead, or is it?
You are sharing. We are seeing your slides now.
Oh, okay.
Perfectly fine.
Okay, I'll just talk through them. So basically, I wanted to start by talking about coarse-grained models. So coarse-grained models describe physics on coarser scales, and they do this by using enhanced equations and parameters in order to account for small-scale effects. So, for example, if I want to know the flow rate through a porous medium, I could resolve the flow field using the Navier-Stokes equation and then average the solution. However, it would be a lot more computationally feasible to actually just use Darcy's law, which relies on the permeability, kind of an effective parameter that tells you about the resistivity of fluid flowing through a medium. And so in using Darcy's law and reducing the computational cost, this kind of idea is very enticing to engineering applications involving porous medium, because there's always complex geometries existing at the micro scale, but we're often much more interested in large scale effects. And so resolving all these microstructures at the smaller scale would be computationally feasible to do if you want to look at, say, a CO2 plume move through the subsurface. So coarse-grained models are often relied upon. But the question is, what about other types of physics besides fluid flow? What kinds of coarse-grained models should you use? So for mass transport or heat transfer. And so one of the answers to this question is you could use upscaled methods, which give you these upscale quantities, or give you these mathematical models of upscaled quantities or average quantities. And these all kind of follow a similar process, which involves defining a representative elementary volume, defining average over that volume, and then the general goal is to average over the equation of a quantity of interest, and basically mathematically derive a second equation for the average of that quantity of interest psi. So one of these processes is homogenization theory. And in homogenization theory, you often assume that your pore scale domain is spatially periodic, which means you can define a unit cell with a length scale smaller than that of the pore scale domain. And if you have your pore scale equation, you can go through this long mathematical derivation in order to come up with a continuum equation, which is an equation for the average of your quantity of interest here being psi. And so what that average kind of pertains to is as if you're moving like a window throughout your pore scale domain about the size of your unit cell, and you were averaging the solution continuously inside of that window. That's what the continuum equation is solving for. And so it does this by using effective parameters that you could see on the screen, namely the effective diffusion, which relies on chi, and chi is called the closure variable. And the way you find the closure variable is through a closure problem, which is provided by homogenization theory. So to use this model, you basically solve the closure problem on the unit cell domain, calculate your effective parameters, and then resolve the continuum equation on the continuum domain. And the advantage of this is that you're going to reduce computational costs significantly because you don't have to resolve all these geometries, and you also have known error, you'll know the error. You'll have a known error threshold within certain physical regimes called, and those are called applicability conditions. The disadvantage to these models is that they're time consuming to derive and they're analytically intractable for complex systems. So for example, if you had a really complex porous network or reaction network in a porous medium with multiple homogeneous and heterogeneous reactions, it might take you a lot of time, mathematical expertise, and analytical intractability in order to derive these upscaled equations. So this is why in the last couple of years, I've been developing this code called Symbolica, which allocates all of this analytical derivation work to computational resources using symbolic computing in order to give you these upscaled models in a very accelerated and automated fashion. So how does Symbolica work? Well, it has two phases. In the first phase, it's called the preparation phase, and you give Symbolica basically just a description of your microscale PDEs. And then what Symbolica is going to do is scale that system given the scales that you provide. And then it's going to find dimensionless numbers within the dimensionless coefficients that it finds. And upon doing so, it will enter the upscaling phase where it'll assign different dimensionless numbers, different values that you provide, which determine the physical regime of the system. And then it will undergo this automated homogenization procedure and provide an output, which is the upscaled equations, effective parameters, and the closure problems automatically. So how do these kind of relate, the PD description and the output, the upscaled output? Well, if I were to solve the pore scale, and it looks like my videos are moving so quickly, but if you were to solve the pore scaled system on, say, like an array of cylinders, what you would find is you'd find this solution that's unfortunately not plane, but you'd find a solution that would kind of like transient kind of dispersion through this network. And the idea is if I were to take a box that's the size of the unit cell and slide it across this pore scale simulation and average the solution, you could get this average pore scale simulation. This is what you would compare to your upscaled simulation, which unfortunately they're not playing, but I promise it looks similar. But the idea is that if I took those two simulations and compared them, I could actually compare at different time steps and find that all the errors throughout the domain exist under this known error threshold. So this means that Symbolica is doing the right thing and we're getting applicable models. So now I want to talk about something more closer to what I've been doing more recently. And unfortunately, again, the slides are kind of clicking, so I'm sorry if there's a lot on the screen, but what I've been doing recently is going through this, developing this generalized closure form strategy. And so what this does is it allows you to upscale and create these models in moderately and strongly reactive regimes, whereas classical homogenization theory was constrained to weakly reactive regimes. And so you can find details of how we do this and automate it with Symbolica in these, the two upper right QR codes for parts 1 and 2 of our preprints. But there's two main results from this. And the first of which is that there's, if you have a microscopic diffusion reaction system and you upscale in the moderately reactive regime, what you'll find is actually macroscopic advection. So what that means is if you provide that system to the left to Symbolica in 15 seconds, it'll provide an upscale equation where you can actually see that there's an effective advection term, even though there's no fluid flow in the system. And you can see at the very bottom that for linear and nonlinear cases, you could see that there's a fluid or effective velocity where there's no fluid flow in the system and can actually be nonlinear. Now, the second part of this that we found is that for multi-component systems, if you upscale them in the moderately reactive regime, you can find immersion terms in your models. So if you upscale the multi-component system using Symbolica, you could see that in the upscale equation for the first concentration, that there's an emergent term that looks very similar to the effective advection term, but the gradient operator is operating on the second concentration. So this is a little bit non-trivial, but we are in fact able to validate this. And you can see that at the bottom left, that the error exists under the known error threshold. So these are two idealized cases that we kind of developed, and then we are able to see these effects. But what about more realistic scenarios? So the first of which I'll present. This is basically a project that I did during the summer with my two undergraduate researchers. And what they're able to do in 8 weeks was go from basically reaction rate laws for CO2 sequestration, hydrogen storage, and basically use Symbolica to develop and validate upscale models for these reactions. And the models that they developed, you can see in the bottom left, were actually incredibly non-trivial. You can see that the emergent terms that came out of this were things that you probably wouldn't be able to guess by just looking at the microscopic description of these equations. So this kind of cautions us that, if we're going to develop an upscale model for this, we might not be able to trust the microscopic description for the form of the model, depending on what physical regime we're upscaling in. Now, the second application that I want to show is basically applying Symbolica to battery module modeling and thermal runaway. So if you're familiar with all the electric vehicles on the road these days, they have these large battery packs on the bottom of their vehicles filled with batteries that can sometimes undergo thermal runaway. And if you're unfamiliar, thermal runaway is when heat is generated by the batteries that are operating. And if the heat is not transferred away fast enough, it actually increases the temperature, which increases the reaction rate, and then therefore it produces more heat. And so this cycle actually causes your batteries to fail. Now, without getting into all the details, what we're able to do with Symbolica is provide for it the conduction, the heat transfer description of this, which is conduction. And we're able to upscale and get this equation on the right that you see, where there's both effective advection, even though there's no flow in the system, and there's emergent terms, which depend on the temperatures of the battery cells. And so unfortunately, again, the videos are not playing, but what I was going to show at the bottom was basically simulations of us able to match basically thermal runaway. So on the right-hand side, the batteries were heating up very aggressively, and a thermal front would be traversing over to the right-hand side. And you would be able to capture all of these gradients with the upscaled equations that Symbolica provided. And in fact, you'd be able to run the models 10 times faster than the Bohr scale simulation. All right, so with that, I'll summarize and say that I was able to introduce Symbolica, symbolic computational code for automated accelerated upscaling. And here we just automated homogenization theory, and you could find more details in our publication. And then I described some of our more recent work, which was developing the generalized closure form strategy, and kind of revealed some of its non-trivial results. And then I showed two applications of Symbolica, one in subsurface reactor transport with my undergraduate interns, and then one in heat transfer with the ion battery packs. And the whole idea of Symbolica is to democratize this model development methods in a similar fashion how computational physics softwares provide access to numerical methods. And so with that, I'd like to acknowledge the team that's been either using Symbolica directly or using the results of Symbolica. And with that, I thank you and look forward to your questions.
Thank you very much, Guy, for this talk. It was a really interesting talk. I will have a question now from the audience, so feel free to ask question in the chat, and we will give them to the speakers. For the moment, I have one, so tell me if I understood correctly, but you are trying to find the symbolic form of the upscaling PDE based on microscopic data, right?
Yeah.
Yeah, it's impressive. And you find that in some models, you get some emergent terms that are not really expected in classical PDE forms of upscale model.
Yeah, so you obtain these terms where they kind of like, instead of usually, we're used to seeing like different differential operators operating on kind of, I guess, the local or the native like dependent variable. So like concentration 1 will have gradient operators on concentration 1, the equation for it. But now we're finding, yeah, if you have the equation for concentration 1, you could actually have gradient operators on all other concentrations and nonlinear combinations of them and things like that.
Okay. That's really an impressive work. Thomas,
Yeah.
did you have any question?
I have a quick question.
Yeah.
It's very impressive, guys. This is like a lot of people in the field see this as like the holy grail, right? Like trying to find the upscaled equations for multi-phase flow in porous media. So I was just wondering if you has this been bench tested against like things that we know the upscaled format from advanced? Like if you started like from, I don't know, single phase flow and Navier-Stokes and so on, could you recover Darcy's law without adding anything extra?
Yeah, well, so we did it in transport, we're able to find kind of like the classical results. I think kind of the idea here is that there's a lot of cases where it's hard to say what the actual form is. So for very simple cases, we've recovered, we've taken a couple of publications and actually been able to recover the results that people have gotten. But then, as we start to bridge further, it actually becomes harder and harder to not to validate, but to, have like a standard, because the standard's kind of unknown. And really all we have to go on is to develop the model and then numerically, test it for different cases. And if it all fits under the theoretical threshold, then, then that's the new standard.
Yeah, super. That's excellent.
So I don't see any question from the audience. So I think we will finish the session here. So thank you again to both of our speakers. So thank you, Kai, and thank you, Joanna. It was really impressive talks, both of you. So I would like to advertise next session for next month. So it will be scheduled on the 15th of November at 3:30 Central European Time, and we will have speakers from Germany and Austria, Supriyan Bashkaran and Umidalisa Amholajvinav. I'm sorry for the names. So thank you again to the audience for joining us today, and please stay tuned for the next Bruce Media Tea Time Talk. And if you have any comments or want to be involved as a speaker, please feel free to contact us at our Gmail address, so brucemedia@gmail.com. And thank you everyone, thank you to the speakers again, and see you next time.